Somewhere in the dark between stars, a fragment of another world drifts through sunlight for the first time. Its dust twists the light into patterns no comet has ever made before, an alien fingerprint written in polarization, color, and memory. Comets have always felt like time capsules drifting through space, quiet, icy remnants from when the solar system was still a messy nursery of dust and gas. They carry pieces of that chaos, untouched, frozen in time. And sometimes, when sunlight hits them just right, they reveal their secrets. Not in color or brightness, but in the way the light twists and scatters off their dust. That twist is called polarization, and it's how scientists read the stories hidden in the glow. Over the last decade, that light has told us more than we ever thought it could. Researchers figured out that comet dust isn't just made of tiny separate grains. It's built from massive clumps of even smaller ones, tangled together like cosmic lint. Modeling these large aggregates finally made sense of everything. Why the polarization changes with angle and wavelength, why some comets look darker or brighter, even why their thermal glow behaves the way it does. But the real breakthrough came when scientists realized comets fall into two families, those with high polarization and those with low. The difference isn't random. It reflects how and where they were born and how long they've been wandering since. And yet, as always in space, solving one mystery opened two more. Some comets' polarization increases with wavelength, others drop off. Nobody's entirely sure why. Maybe their grains are structured differently, maybe they're mixed with different chemicals. Then there's the faint circular polarization, a barely there signal that seems to spin the light itself. It's been found in a few bright comets, and some suspect it's caused by organic molecules arranged in a specific handedness, the same kind of asymmetry life on Earth depends on. If that's true, comets aren't just time capsules. They're messengers from before biology even began. What makes all of this trickier is the role of big dust grains, the heavy hitters in a comet's halo. Tiny particles outnumber them by far, but the large ones have far more power over how light behaves. When scientists model comets, they use something called the discrete dipole approximation to simulate how irregular particles scatter light. Those simulations showed that leaving out the largest grains doesn't change how bright the comet looks much, but it completely warps the polarization curve, especially the weird little dip near 0 degrees called the negative branch. That dip disappears unless you account for big, less absorbing grains. It's proof that brightness alone can lie. You need the polarization to see what's really there. Then came 3I Atlas, the third interstellar object ever confirmed, a visitor from another star carrying dust not born under our sun. And when astronomers turned their polarimeters on it, they found something completely new, a deep, narrow negative polarization branch sharper than anything seen before, bottoming out at negative 2.7%. That kind of signature doesn't belong to our kind of comet. Its grains were darker, denser, maybe compacted by another star's light and heat long ago. The usual comets invert around 20 degrees. 3I Atlas flipped at 17. It was small detail, but one that spoke of another world's chemistry, another kind of dust. Images showed no dramatic jets or structured coma, just a smooth, uniform haze. Its behavior didn't quite match asteroids or trans-Neptunian objects either. It was something in between, and yet apart. Theories pointed toward coherent backscattering, light bouncing around inside big dark grains and reinforcing itself on the way out. Whatever the exact mechanism, it meant this comet wasn't made of the same stuff as ours. It was a whisper from another solar system, speaking a slightly different optical language. 3I Atlas changed the game. Polarimetry, once a quiet corner of comet science, suddenly became a bridge to the stars. What we learned studying Halley and Hale-Bopp and the rest now helps us read the dust of interstellar travelers. And with new telescopes like the Vera Rubin Observatory about to scan the sky every night, we'll soon see thousands of them. Each one a drifting clue to how other systems form and die. The light they scatter tells us something universal, that whether it's a relic from our own beginning or a stranger passing through, every grain of dust remembers the story of where it came from. Together, those findings reframed what we thought comets could be, proof that chemical diversity stretches far beyond our solar blueprint. But while Webb was studying a traveler from beyond, another spacecraft, long gone now, had already revealed what our own comets had lost. When Rosetta and its lander Philae descended onto Comet 67P, scientists expected to find the fingerprints of magnetic fields locked inside. Remnants from the magnetic fog that once surrounded the newborn sun-iron minerals, like magnetite, preserved in meteorites, hinted that the first clumps of dust were drawn together by invisible lines of force. But as Philae bounced and settled across the surface, its instruments kept reading nothing. No increase in magnetic strength, no internal field waiting to be rediscovered. Whatever magnetism once existed had vanished. Rosetta's orbit confirmed it. The faint fields dancing around 67P were from the solar wind, not the comet itself. Somewhere between pebble and planet, the magnetic memory of creation faded. Gravity had taken over, and the dust that once responded to magnetism grew too heavy to care. Comets, it turned out, might still carry the chemistry of the beginning, but not the magnetism that once stitched it together. They were ancient, yes, but magnetically dead. It's a strange duality, one comet carrying alien chemistry, another whispering silence where magnetism used to hum. And yet together they complete the picture. The Rosetta Comet shows how the early solar system outgrew its magnetic blueprint, while 3I Atlas shows that somewhere else, the ingredients of creation followed a completely different script. Dust, ice, magnetism. Each leaves its own kind of fossil, and together they reveal that world building isn't a single story, but 1,000 variations on a theme. Our comets remember in silence, theirs speak in carbon. Both drift through space as proof that every star writes its own version of how life begins. And then came the colors, or at least the rumors of them. Some astronomers swore they saw a faint green shimmer bleeding through the coma of 3I Atlas. Others whispered about strange metal emissions, the kind you'd expect from nickel or iron rather than dust and gas. It was hard to tell what was real and what was wishful reporting, the kind of story headlines like to exaggerate. Still, the possibility hung there, glowing faintly at the edges of the data, daring scientists to look closer. What could be verified was already strange enough. As the comet inched closer to the sun, its color began to shift, slowly, then unmistakably, from a deep red hue to something more neutral, almost solar in tone. In plain terms, it brightened fast, its surface dust shifting from weathered reds to glassy neutrals. Spectra in the visible bands showed a slope similar to the reddest asteroids out past Jupiter, the D-types, whose surfaces are painted in ancient carbon and organic residue. But 3I Atlas wasn't staying red. Its light was flattening, brightening, turning almost neutral, as though something fresh had been released beneath its weathered surface. Fine, icy dust can do that. Tiny, reflective grains scattering sunlight like frost on glass. The larger, older grains, coated in dark tholins or metals, tend to swallow light and give everything a rusted tone. If the comet was shedding its old skin, that color shift might have been the first hint. Still, the mystery deepened with each observation. If the greenish tint was real, it might have come from excited molecules like CN or C2, the same gases that make some comets glow emerald near the sun, or maybe from metallic elements we haven't seen behave this way before. But if it was just the product of smaller, brighter grains taking over the light, then the comet was simply revealing a younger, cleaner face to the solar wind. Either way, the evolution of its color and reflectivity didn't fit neatly into the patterns known from solar system comets. It was as if the rules were slightly off, as though its dust was made from a recipe we'd never tried before. That's the strange beauty of something that came from elsewhere. Even its light doesn't behave quite the way we expect. For now, scientists are holding off on the more dramatic claims. The green metal plume headlines belong more to tabloids than telescopes. The truth will come from better data, from the careful mapping of its albedo and color as it swings past the sun, because somewhere in those shifting shades, from red to neutral, from dull to glinting, lies the fingerprint of what interstellar dust really is. A small clue, drifting through our sky, hinting that even the color of sunlight on a comet can carry the memory of another star. Somewhere between fact and imagination, scientists began to trace where 3I Atlas might have come from. Its path through the solar system wasn't just unusual, it was impossible to belong here. The trajectory was hyperbolic, the speed too great, the orbit open-ended. It wasn't circling our sun, it was passing through, a messenger from elsewhere, destined never to return. Its motion hinted at an origin far older and colder, a region in the thick disk of the Milky Way where ancient stars burn faintly and metals are scarce. That made sense. Its chemistry, its color, its strange behavior all seemed like the fingerprints of something that formed under different rules. If it really did begin in a low metal world, then the dust it carried would have grown differently from ours. Maybe its grains were smaller, denser, their surfaces sculpted not by warmth, but by long silence. Maybe the minerals inside them had refractive powers we don't yet recognize, bending light in ways that made its glow seem alien. Its CO2-dominated coma fits that picture too. It could have formed beyond the carbon dioxide frost line in its parent system, where CO2 ice stayed solid while water remained gas, flipping the chemical balance we consider normal. Each clue, polarization, chemistry, color, aligns into one picture, a world built under different rules. In a way, 3I Atlas might be showing us not what went wrong, but what else is possible. No one knows which star cast it off or when. Maybe it was born in a system long gone cold, orbiting a red sun that's since dimmed into obscurity. What we do know is that every number, every spectrum, every odd curve in its data is pointing toward the same idea. This comet is a relic from a completely different kind of protoplanetary disk, one that played by unfamiliar rules, that thought lingers like static in the signal, waiting to be confirmed. Future missions will chase it with sharper instruments, measuring the size of its grains, retracing its journey through galactic space, trying to locate its lost home. Until then, 3I Atlas drifts on, carrying the proof that even in something as simple as dust, the universe remembers the diversity of its beginnings.